Good morning, sir. My topic is synchronous and asynchronous counters in space electronics. Myself, Breach Patel. I am from IT2 department. My enrollment number is 2480063. So, my this presentation explores the crucial role of synchronous and asynchronous counters in space electronics. We will cover the fundamentals of each type, their operational differences, and the specific applications in space missions ranging from high precision timing to lower power subsystems. This knowledge is essential for engineers and designers involved in aerospace technology. So, in digital systems, counters are indispensable components used for event counting, precise timing, and logic sequencing. Their adaptability is vital for various applications from simple clock functions to complex data processing. Synchronous counters and asynchronous counters both have unique advantages and applications, especially within aerospace systems where precision and reliability are key. Their section outlines are the fundamental function of counters and their significance in model systems are event counting, precise timing, and logical sequencing. So, what is counter? A counter is a digital device fundamentally designed to store and incrementally count pulses in binary format. This component captures and tracks recurring inputs, converting them into digital representation that can be processed or analyzed. This function in critical is in systems that require precise tracking and control based on input frequency. Counters are essential building block of digital electronics plays a significant role in almost any system like binary storage, pulse counting and digital conversion. Types of counter. Counters are broadly categorized into two primary types based on their operational mechanism. They are synchronous and asynchronous counters. Synchronous counters have all their flip-flop triggered simultaneously by a common clock signal, enabling precise timing and coordinated operations. In contrast, asynchronous counters operate with each flip-flop triggering the next and creating a ripple effect. Synchronous counter. In a synchronous counter, all flip-flops are triggered simultaneously by a common clock signal, and the decision ensures that all output change at the same time, which is essential applications requiring precise timing coordination. Synchronous counters are more complex to design, but they offer superior speed and accuracy compared to asynchronous counters, like common clock, simultaneous change, and its complex design. Asynchronous counters, in contrast to synchronous counters, asynchronous counters have flip-flops. They are triggered one after another, creating a ripple effect. Each flip-flop's output serves as a clock signal for the next flip-flop in the sequence. Asynchronous counters are simpler to design than synchronous counters, but suffer from propagation delays, which can limit their speed and accuracy. Asynchronous can rely on a rippling clock signal, have a simpler design. Now, basic working of synchronous. Synchronous counters ensure that all outputs change simultaneously by a common clock signal to trigger all flip-flop at once. This simultaneously triggering eliminates the propagation delays seen in asynchronous counters, providing more precise and predictable timing. This is particularly crucial in high-speed digital systems. Basic working of asynchronous counter. In an asynchronous counter, each flip-flop output serves as a clock signal for the next flip-flop. This creates a ripple effect, where the change in one flip-flop triggers the next. Asynchronous counters are simpler to design, but slower due to cumulative propagation delays as the signal propagates through the chain flip-flops. Asynchronous counters use a ripple effect for clocking and have simpler designs with inherent delays. Application in space. Synchronous counters are essential in space applications that demand the high precision and coordination operations. They are commonly used in telemetry systems for accurate data transmission, in data signal processing like DSP for real-time data analysis, and in error correction code due to timing and ensure data integrity. The ability to maintain synchronization is crucial for mission critical tasks. Application of asynchronous. Asynchronous counters find their niche in space applications where low speed and low power consumption are prioritized. They are commonly used in basic timers, watchdog timers that monitor system health and low power subsystems. They do not require high-speed operations. Their simplicity and minimal power usage make them ideal for secondary or monitoring functions. They are low speed, low power, and they are simple timers. Asynchronous versus synchronous counters in space electronics. Now, advantages of using synchronous counters. Due advantages like they have high speed, they have accurate timing, and they have less timing error. Advantages of asynchronous counters. They have simple design and they consume low power. Now the thing of disadvantages. So in the disadvantages, synchronous counters have low complexity and their power consumption is very high. Now, disadvantages of asynchronous counters are they have very minimal amount of speed, they are cascading interrupt delay and the propagation delay in which the timing error increases with the number of more flip-flops. Asynchronous versus synchronous counter comparison, due to which the characteristics like speed, accuracy, design and power. So the speed of synchronous is high, accuracy is high, but in design asynchronous is simple and the power supply is low than the synchronous. Radiation effect on counter design. Space electronics face consistent radiation exposure which can cause simple event upset SEUS and other malfunctions. Synchronous design may reduce timing errors induced by radiation while asynchronous designers may offer inherent robustness due to their simpler structure. Mitigation techniques such as radiation hardening and error correction codes are crucial for both counter types. The choice between synchronous and asynchronous designers must consider the radiation toleration and the effectiveness of mitigation strategies. They are mitigation timing errors and potential robustness. The significance of counter in space applications. So, due to which they have precise control, event counting, and system reliability. So, applications span from controlling satellite thrusters to managing data acquisition from sensors. Their ability to maintain accurate timekeeping and event tracking makes them indispensable components of space systems. These components ensure that the critical operations occur at precisely at the right moments. Now, real world example is satellite thruster control. So, synchronous counters are frequently employed in satellite thruster control timing. Precise timing is essential for executing maneuvers correctly and maintaining the satellite's orbit. The accuracy of synchronous counters ensures that the thruster pulses are delivered at exact intervals. Variation in timing can cause deviations from intent trajectory, wasting fuel, and impact the mission's goal. Robust and reliable counter design is crucial for mission success in these critical applications. This example demonstrates the importance of carefully selecting the right technology. 1. Precisely timed pulses. 2. Maintaining orbit. And 3. Maneuver execution. So, key design consideration for space counters. When designing counters for space application, radiation hardness, power efficiency, and striking timing requires must be carefully considered. Each factor is significantly impacts the choice between synchronous and asynchronous designs. Addressing these challenges ensures a robust, reliable system. Due to their radiation hardness is high, their low power efficiency, and their main thing is precise timing requirement. So now synchronous versus asynchronous counters in space electronics. This will can help us to analyze their advantages, disadvantages, and applications in the challenging environmental of space. By understanding these differences, engineers can select the optimal counter design for robust and reliable space missions. Advantages like high speed, accurate timing, and less timing error are the synchronous counters. They are often choice in scenarios while timing accuracy outweighs and design simplicity, and their capability to maintain precision under varying conditions is vital for reliable performance in space mission. High clock speeds or reduced timing skew are benefits. Synchronous counters are offer distinct advantages for applications requiring high precision and speed. The design ensure all flip-flops are clocked simultaneously, reducing timing errors and enabling accurate event counting. Thank you, sir.